Hey guys, it's Virginia, here to go over practice exam 3A. This is my first time recording something like this, so I naturally drew a flower. And in case you want to get in contact with me, you can either catch me at lecture, at one of my sessions, or office hours, or you can email me at this email here, brg5018. So I know that it's really tempting with these videos to sit back, listen to my buttery smooth voice, and not get out paper or anything and just watch as I go through the problems. But it'll be a lot more beneficial to you if you've already looked through the exam and you take notes as you go along. Okay, so get out that paper, pencil, and your Chem 112 approved calculator. Okay, let's do it. So the first problem on this practice exam is about hydrogen peroxide, and they're asking us to figure out what the oxidation state of the oxygen is in hydrogen peroxide. So let's start with the formula, H2O2, which was given, and then think about what oxidation states are. We know that it's a way for us to keep track of electrons. And we also have some suggested oxidation states. So we know that the alkali metals, which are things like sodium and everything else in its column on the periodic table, have an oxidation state of +1. The alkali earth metals, like magnesium, calcium, etc., have a suggested oxidation state of +2. Fluorine has a suggested oxidation number of -1. Hydrogen is usually +1. Oxygen we usually consider to be -2. And then the rest of the halogens are -1. And so you might ask why I wrote it this way, why I didn't put fluorine in with the other halogens. And part of that is because the way I've written it ranks them in terms of strictness. Okay, so the alkali metals will always have an oxidation number of +1. Whereas hydrogen is usually +1, but if you were to pair it with something higher than it on the oxidation table here, it would adjust to satisfy the alkali metals, the alkali earth metals, and fluorine. Okay, and so we'll see here, we take our hydrogen peroxide, and we look at this chart, and we see that the most strict atom we have here is hydrogen, and that it's going to be +1. So we can go ahead and assign hydrogen an oxidation number of +1, making it overall +2 because we have the two hydrogens. We also know that the sum of the oxidation numbers need to equal the charge on our molecule. And so our molecule's charge is 0. It's neutral. So if we have +2 from the hydrogens, we know from the total of the oxygens, we need to have -2. And since we have 2 oxygens here, we know that it will be -1. Okay. And so we see here that because we started with hydrogen, which is the more strict atom, that the oxygen did have to adjust from its preferred state to make this peroxide. And that's a trend for all peroxides too. And so the correct answer here will just be D. Okay. Now moving on to number 2. We have a question about a weak acid, and I always think it's a good idea to start by just writing the formula, the equation. So HA in water will have an equilibrium with H3O plus and A minus. So we have to stop and think about what it means to be weak. Okay, the question is more conceptual than asking us to solve the pH, and they don't give us a Ka. But something we know because it is weak is that our Ka is going to be a lot less than 1. And so that tells us that the concentration of H3O plus times concentration of A minus divided by the concentration of HA is going to be a lot less than 1. So if we go through the answers, the first says that the pH of solution is going to be equal to 1. So that would be true if this were a strong acid, but this is a weak acid. So to really be able to decide what the pH is, we would need the Ka, and we would have to ice it out. Okay, for B, say that the concentration of this HA is going to be a lot more concentrated than the A minus. So if this expression we have is true, which we know it is because it's a weak acid, to make it less than 1, we would have to have a lot of HA. More HA present in solution than the hydronium or the A minus. Okay. So that tells me that the second answer seems to check out. But if we look at C, it suggests that HA would be equal to A minus, and that wouldn't be true either, because we know with the weak acid we're just getting a little tiny amount of dissociation, making C and D false. E could be confusing because we know actually that the amount of A minus is equal to the amount of H3O plus, but that's different from hydroxide. And we don't even have hydroxide in our expression here, so we can cross that one off, making B the correct answer. And that will be true for any weak acid. Okay, so this one's more conceptual. For number 3, we have another conceptual problem. They're asking us how the pH would change for 3 different solutions when adding water. Okay, so when we add water, what we're essentially doing is diluting them. So we're diluting the solutions, which means that everything in it is going to be less concentrated. Hopefully this problem doesn't make you guys less concentrated. Okay, so let's think about what kind of solution we have for our first one. So we have KCl. We can then stop and think, does potassium affect the pH? No, right? Spectator. Does chloride affect the pH? Nope, it's another spectator. So this solution would be neutral. And adding water to that isn't going to change that. It will just continue to be neutral. So we know that this will have no change in pH. Okay, now looking at the second problem, HCl, that's a strong acid. Okay, so we know acids lower the pH. And so if we dilute the HCl, Now it will be less concentrated. So if we were to make it less concentrated, we also make it less acidic. And you can do the math for this. But if you know that this is an acid, it's less concentrated, it will be less acidic. Less acidic would correspond to a higher pH. Okay, and we'll see a similar trend here with the KOH. We have a strong base. And if we dilute a strong base, we'll make it less basic because the OH minuses will be more dilute. And if this is less basic, then we're going to have a decrease in the pH. Okay, so with the first solution, we're starting neutral, keeping it neutral. With the second problem, we're starting acidic and raising the pH to bring it closer to neutral. And with the KOH, we're starting basic and lowering the pH to bring it closer to neutral. And so the correct answer here ends up being B. Okay, so for number 4, they're asking us to figure out the solubility of cadmium hydroxide. They give us a specific pH, and they give us the equilibrium constant for the dissolution. Let's start by writing the expression, or the equation for the dissolution. So cadmium hydroxide, solid, right, because we're trying to dissolve a solid in water, is in equilibrium with cadmium ions, which are now aqueous, and 2 hydroxides. Okay, so they give us the KSP, but let's go ahead and write the equilibrium expression for that value. So we got a little lazy with acid-base chemistry and their equilibrium expressions. We'll have to be more careful here because we don't want to include the solid, and we'll have to pay attention to the stoichiometry with the hydroxide. So our KSP will be the concentration of cadmium ions times the concentration of hydroxide ions squared. And so we have something that's weakly soluble, and so we can borrow some of our tricks from acid-base chemistry, though, and think about how we start initially, how things change, and what we end up with at equilibrium. So as the saying goes, when in doubt, you say it. When in doubt, ice it out. When in doubt, ice it out. Okay. So, we're going to ignore the cadmium hydroxide in our ice table. Why, you ask? Because it's a solid. So initially, we don't have any cadmium ions in solution. But we do have some hydroxide ions. Okay, so we're in water. So we have to consider the pH of our solution. They tell us here that the pH is equal to 9. But we don't care about hydronium, right? We care about hydroxide. So we want to know about the POH. And we know that's going to be 14 minus 9, which is equal to 5. We care about this because 10 to the power of the negative POH, which is 5, is going to be equal to our hydroxide concentration. And so this will be the initial value that we use up here. Okay, so now that we have that set up, we can do our plus x, x, 10 to the minus 5 plus x. And then now we can use our KSP expression. Okay, get rid of this. Okay, so we can go ahead and put in x for our cadmium concentration, and 10 to the minus 5 plus x squared for our hydroxide concentration. Okay. But when we do this, we know that we can ignore the x that we're adding because our KSP is so small. It's 10 to the minus 14, so this change will be insignificant. So we can get rid of the plus x and just set up the expression that KSP, which is 2.0 times 10 to the negative 14 is equal to x times 10 to the minus 5 squared. And then we find, after plugging into our Chem 112 calculator, that x is equal to 2 times 10 to the minus 4 molar. Okay. And you have to be careful with the square, because if you lose track of your square, you'll end up with B instead of A. Okay, so here A is the correct answer. Okay, so we are still doing equilibrium. It's just now we have a slightly different system. Okay. For number 5, a lucky researcher gets to perform a titration. And they generate this curve. And we're supposed to decide what kind of solutions we have. So I think it's important to think about how we're starting with some solution A in our beaker. And then we're adding B. And so our starting pH, if we look here, is less than 2. That's a really low pH. So A must be an acid. And that would make B a base. And that's just a happy coincidence in terms of like B for base and A for acid. Because if we had started with a pH of like 13, then A would be a base. Okay. So we know that A is an acid. We're adding base, and we look at the shape of the titration curve to figure out whether it's strong or weak. And so if you look at this region here and how just extended it is, we can see that this is what we'd call the buffer region, or the buffering region. And they kind of warned us about this in the prompt too. And we know that to be a buffer, you have to have something weak and its conjugate in solution. And so I would say that this is a weak acid and we're adding a strong base to it. If it were a strong acid and strong base, then we would have that like really steep kind of S sigmoidal shape. Okay, but this drawn out region shows that something is weak. So here at the half equivalence point would be the pKa. And the equivalence point is here where we have the inflection. Okay, easy stuff. If you see the drawn out region, weak. Okay, with number 6, we're dissolving some salts in water, and they want us to figure out which will increase the pH. So increase pH, that tells us that they would need to be bases. Okay, so for the first one, we would have KBr. And KBr, when it dissolves in water, you end up with K plus and Br minus. And those are both spectator ions, and so these are negligible. So dissolving KBr in water won't do anything to the pH. For KCN, when we dissolve that, we get K plus, which we already know is negligible, and Cn minus. Let's see. So Cn minus, what's that? The deal with that? If we add a hydrogen, we end up with HCN. And HCN is a weak acid, therefore making its conjugate a weak base. So that tells me that Cn minus is going to be a weak base. WB. And a weak base will increase the pH. Okay, so KCN seems like a good option. If we look at FeBr3, we would get Fe3 plus and 3Br minus. So Br minus is spectator. Then we have to think about the iron and what kind of species iron is. And this is kind of an exam to throw back. But iron is a transition metal, and we talked before exam 2 about Lewis acids and bases. So iron 3 plus is a Lewis acid, and so it will have an effect of decreasing the pH when dissolved. Okay, so don't forget previous material. We're going to keep building on it. Okay, so our fourth salt is NaClO4. And so it will dissociate into sodium ions and ClO4 ions. So sodium would come from sodium hydroxide, which is a strong base. So sodium is going to be negligible. And the ClO4 minus ions, or perchlorate ions, come from perchloric acid, which is a strong acid. So those are also negligible. So dissolving this will have no effect on the pH. Okay, last one is NH4 Br. We'll make NH4 plus and Br minus. So we decided that Br minus is negligible, comes from HBr, a strong acid. So that leaves us with these NH4 ions. And so those would come from NH3, right, when ammonia picks up a proton. And we know that ammonia is a weak base, so that means its conjugate is going to be a weak acid. So that would decrease the pH when dissolved. Okay, so it seems like the potassium cyanide's the only salt that would give us a basic solution. And if you want to see the reaction for that, we can take the cyanide ions, mix them with water, and the cyanide will take a proton from the water and leave hydroxide behind. Okay, so the answer here is D, only that potassium cyanide. Okay, here they're asking us about water. So we know the only thing that can change equilibrium constants is a change in temperature, really. And so they're asking us about how the water will change with temperature. So let's write the equilibrium for the auto-dissociation of water. We have our good friend water dissociating into H plus and OH minus. Okay, and we know that our Kw, which is just the equilibrium expression for this, is going to be equal to H plus times OH minus. Okay, and we also know that to get our Kw from pKw, that we would just take 10 to the minus 12.7. Okay, and if we look at the stoichiometry of this also, we know that the concentration of H plus is going to be equal to the concentration of OH minus. So we could kind of say that this is equal to x squared, where x is just equal to each of those concentrations. So if we take the square root of the 10 to the minus 12.7, we get x. And they're asking us about hydronium ion concentration, which is synonymous with the concentration of H plus ions. And when you do that computation, you end up getting 4.46 times 10 to the negative 7. Okay, which rounds to be the same as answer B. So for number 8, they're asking us to calculate the percent ionization of a phenol solution in water, given a specific pH and the Ka for the molecule. So let's remind ourselves what percent ionization even means. The way that I think about it, percent ionization is equal to the amount of protons we get, the protons that we actually get, versus or over the protons that we would get if we had a strong acid. Which we don't, but. And then the classic times 100%. Okay. So, let's figure out what protons we get. We can write the reaction. Okay. And we could go through and ice it out. And as much as we enjoy ice tables, we actually don't need to employ one here because they tell us what the pH is. And if they tell us what the pH is, we can figure out what our concentration of H plus is. So our concentration of H plus is just going to be equal to 10 to the power of negative 5.07. That's our pH. And we get an H plus concentration equal to 8.51 times 10 to the negative 6 molar. So that will be our numerator there. Okay, so what about the denominator? What about our H plus if it were strong? So for the denominator, we just pretend that we live in this fantasy world where this would go entirely to the products. Of course, it's a fantasy. But in that world, we would have a 1-to-1 ratio between our phenol and our protons. And so in our strong world, our concentration of the phenol would be equal to our concentration of protons. So our denominator concentration would just be that 0.56 molar. Okay, so we can go ahead and do our percent ionization equal to 8.51 times 10 to the minus 6 molar divided by the 0.56 molar, then times 100. And when you work that out, you get the answer to be A. Okay. Okay, so number 9 is asking us to figure out the KEQ for this reaction. And we have a bunch of nickel complexes in here. Don't worry, this problem isn't that complex, okay? So, what we do is just look at the K's they give us. And then figure out if there's some way, like we used to combine those K's to make a new one for this overall reaction. Okay, and it's important to remember that Kf stands for K of formation. So these are the equilibrium constants for when we form these species. So, for the first Kf, we'd have Ni2+ reacting with the 6 ammonia to create that nickel ammonia complex. And that results in a Kf. And then our other Kf would be nickel ions with this En ligand coming together to form the nickel En complex. And that has some Kf to describe it. And maybe now that these two reactions are written next to each other, you can see that they have a lot of the components of the top reaction. So we just have to figure out if there's some way that we can combine these two reactions to make the top. And it's not actually that bad, right? So if we look up here, the En is a reactant, so we want this to be a reactant. And it already is, so that's cool. And we want the nickel ammonia complex to be a reactant. And right now it's written as a product. So all we're going to do is flip that equation over. And now we'll have nickel ammonia 2 plus okay, so now we have our reaction flipped over. So we need to do the same thing to our Kf. So the K for this new reaction that I've written is going to be 1 over the Kf we were given. Okay, so now if we look at the bottom two reactions, we can cancel the nickel. And then what we're left with is just the equation at the top that they're asking us about. So when we need to combine K's, do we add them? Nope. Do we subtract them? Nope. Do we multiply them? Yeah. So we'll just have to multiply these two together. So we'll have 6.8 times 10 to the 17th times 1 over 1.2 times 10 to the 9th. And when you go ahead and evaluate that, you'll get B, which is the 5.7 times 10 to the 8th. Okay, so an old concept, right, with combining equilibrium constants, but just with a slightly new application. Okay, for number 10 here, they want us to calculate the pH of a 0.02 molar solution of barium hydroxide. So we have to think about what kind of compound barium hydroxide is. One clue, in case you haven't memorized your strong bases, which you probably should, is that they didn't give us a K. And that's because we know that it dissociates completely. And we'll have barium hydroxide, big arrow, becoming Ba2+, and 2 OH-. Okay, so we can use the hydroxide to help us figure out the pH, but we need the concentration of hydroxide. And this we can figure out Chem 110 style. So we know from the concentration that we would have 0.02 moles barium hydroxide in 1 liter, and that for every mole of barium hydroxide, we get 2 moles of hydroxide out. So we would have a 0.04 molar OH- solution. Okay, so now that we know the concentration of our hydroxide, we can figure out our POH by doing the negative log of 0.04, which is equal to 1.4. So, would you go ahead and circle B? No, don't do it, because this is POH. Okay, so it's good to stop and think about what you're doing before you just bubble in your Scantron. Okay, so our pH is going to be equal to 14 minus 1.4, which then will be equal to 12.6. And this checks out because we have a strong base. So we expect to have a high pH. Okay, so then that makes this problem A for the correct answer. Okay, number 11. We have sodium chloride and HClO2. Okay, so they're asking about what happens if we add the sodium chloride to this. And this is a weak acid. So we can write an expression for its dissociation. So when we look at the sodium chloride, we know that in water, it will totally dissociate into sodium ions and ClO2 ions. So this 0.5 moles that we're adding will contribute to this side. Okay, so we're adding in a product. And Le Chatelier does not go away, right? We add in more of a product, we'll shift toward the reactants. So if we look at the answers, H plus would increase. That one's going to be false because when you shift to the left, the H plus concentration will decrease. So that's out. pH would increase. Well, as we just said before, we're going to decrease our H plus concentration, so the solution would become less acidic, and when that happens, pH increases. So that one checks out. HClO2 increases. That's true. OH minus would increase. So that one is also true because we know that 1 times 10 to the minus 14, or kW, is going to be equal to concentration of OH minus H plus. So if we decrease H plus, like we discussed, we would have to increase OH minus. So basically, if you're less acidic, you're going to become more basic, is all we're saying. And so 4 would be true too, making the correct answer here D. Okay, so here in number 12, we have a titration problem with a weak acid, acetic acid, and a strong base, potassium hydroxide. So let's start by writing the reaction between them. And so for the strong base, we know that the potassium is a spectator and is negligible, so I'm going to write it just as OH minus for simplicity. And this will totally react to form the acetate ion and water. Okay, and they give us various amounts of these species. But whenever we're doing a reaction, we want to compare things in terms of moles when we're comparing different species. And so instead of an ICE table here for reactions, we want an ICF table. And so just as a quick throwback reminder as to how to get moles from molarity in a volume, you would start with your volume in terms of liters. Okay, so the 50 mils of the acetic acid would be 0.05 liters. And the concentration tells us that we have 0.25 moles in every 1 liter. And so we can see the liters cancel, leaving us with 0.0125 moles of the acetic acid. So we can go ahead and put that in for our initial value here. I'm not going to write out how to get moles for all of the others, but it would be the same kind of process. So for OH minus, we'd have 0.001 moles. Then our initials for these are just going to be 0. So in this reaction, we can think about which is our limiting reagent. So which will we use up all of first? And we just have a reaction that's 1-to-1. So we'll just choose the species with the fewer number of moles, which is the OH minus. And so we're going to use up all of the hydroxide. So we'll have subtracted 0.001. And we'll lose that same amount from the acetic acid. Oh, I'm sorry, this should actually just be 0.01. Okay, my bad, just 0.01. So that will leave us on this side with 0.0025 moles of the acetic acid. And we'll know that we will have gained 0.01 moles of the acetate. And so I know that I started by writing 0 for the water here, but in these we just kind of ignore the water again because all of this is contained in water, and any water that we would make here is going to be negligible compared to the total volume. Okay, so the question is asking us to pick which species are present in significant amounts after this reaction, where we've added 40 mils of the KOH. And so then we just pick anything that's not 0. So we have some amount of the acetic acid still, no hydroxide, and we have acetate. Okay, so we would have both of these first two species, making this answer D. Okay, so for number 13, they're asking us to figure out the pH of a weak base solution. So we have this aniline, which is a weak base. And we can know that by looking at the nitrogen and seeing that we have a nitrogen with 3 groups attached, which makes it a weak base. But also, they gave us a Kb, which is kind of a hint that we'll have a base reaction. Okay. So let's start by writing the reaction. C6H5 NH2 plus water be in equilibrium with the protonated aniline and hydroxide. Okay, and as we all love to do, we need to ice it out. Each time's like the first time, isn't it? New and exciting. Okay, so our initial concentration of the aniline they give us as 0.5 molar. We're going to ignore water. They don't tell us anything about these two species. We'll have minus x plus x plus x. Okay, that's great. But let's think about what our Kb is even telling us. So Kb is going to be equal to the concentration of OH minus times the concentration of the protonated aniline divided by the concentration of the aniline at equilibrium. So we know that this is 3.8 times 10 to the minus 10. And that's going to be equal then to x squared over 0.5 minus x. And we're going to ignore that minus x because we have a small enough Kb. We'll multiply over and then take the square root to find that x is equal to 1.38 times 10 to the minus 5. And I like to stop and remind myself what that x even is. So that's the concentration of OH minus. And from that, we can easily get the POH by taking the negative log of this value and find that POH is equal to 4.86. We know that pH then will be equal to 14 minus the 4.86, thus making it 9.14, which is A. Okay, so with a weak base, you can still ice it out. Just don't forget when you're writing your reaction to include water. Okay, that's how you get the balanced reaction with the hydroxide. With number 14, they're asking us about Todd's favorite thing, buffers. Okay, so let's remind ourselves what it takes to be a buffer. You need something that's weak, and you need to have its conjugate. That's the only qualification. You need a weak acid or base, and then its conjugate base or acid. So let's go through these individually. So here we have HF, weak acid, seems promising. And then we have sodium fluoride. So sodium fluoride, we know when it dissolves that it would give us fluoride ions. And fluoride is going to be the conjugate base for HF. Okay, so we'll have HF dissociating into H plus and F minus. So we have both of those things. So we have a buffer. Easy. Okay, for the second one now, tell us we have ammonia and ammonium chloride. So we know ammonia is a weak base. And with water, it reacts to form NH4 plus and OH minus. And the NH4Cl will give us this NH4 plus. So again, we'll have both the weak base and its conjugate acid. Buffer. Okay. The next two are a bit more complicated because we have something weak mixed with something strong. So I'm going to get rid of these equations. Okay, so here we have HCl and NH3. So let's start by writing the reaction between them. Okay, cool. Whenever we have a reaction, we want to consider the moles involved and make an ICF table. Okay, so under these conditions, we would end up with 0.025 moles of the ammonia and 0.1 mole of the HCl. We'd start with none of these. And then we have to think about the limiting reagent. And in this case it will be the ammonia. So we'll use all of that up. Have minus 0.025 minus 0.025 plus 0.025. Leaving us with 0.025 of both of those. And then we'll have 0.975 for the HCl. So now at this point, we can stop and say, do I have both the weak species and its conjugate? And in this case, that's not true. We have the conjugate, but we don't have any of the weak species. So this would not be considered a buffer. Okay. And so for the next scenario, we'll have to take a similar approach because now we have a strong base and a weak acid. Okay, so let's write the reaction. We'll have HF And again, for the strong base, I'm just going to write OH minus. That will react to form F minus and water. With the reaction, I'm going to compare moles again and make an ICF table. So for the HF, we'll have 0.025 moles. For the hydroxide, we'll have 0.1 moles. 0 for these guys. Our limiting reagent is going to be the HF. We'll use up all of that. We'll take that much from the hydroxide. And on this side, we'll make that much of both of these. So we'll have 0.975 moles of the hydroxide left, and we'll have made 0.025 moles of the fluoride. Okay, so again we stop and think, do I have something weak and its conjugate? Well, we have the conjugate. Again, we don't have the weak acid. Okay, so this would not be a buffer. Okay, so that makes D the correct answer here. Only 1 and 2 make buffers. So whenever you have something like this, where you have something weak reacting with something strong, you need to make sure you have excess of the weak. And then you'll have a buffer. Okay, but writing out the ICF tables helps you see that. Okay, well, if you had started to get bored, don't worry, because I'm going to draw your attention back because we have another titration problem. So we have benzoic acid and sodium hydroxide. They give us a Ka. And we have to find pH at the equivalence point. Okay, this is going to get kind of long. But as Todd has said, these are the boss fights of acid-base chemistry. Because you've got to write a reaction. You've got to ICF it. Then you've got to take something and get concentration, and then you've got to ice it, and then you've got to flip your K, and then you've got to keep going. Okay. So let's do it. We have benzoic acid. Write our reaction. C6H5COOH plus OH minus. Again, I just took OH minus from our strong base. Well, C6H5COO minus and water. Whenever we have a reaction, we're going to work in moles and use an ICF table. Okay, so I'm not going to show the calculation, but we know how many moles of the benzoic acid we have because they give us volume and concentration. And they tell us that we're going to add as much NaOH as it takes to get to the equivalence point. And all the equivalence point is about is that your moles of acid need to equal moles of base. Okay, equivalence point equal, so on. Okay, so if we can figure out from the volume and the concentration of moles of benzoic acid we can figure out how many moles of NaOH we would need to have. So this works out to be 0.09 moles of the benzoic acid. which means that we need to add 0.09 moles of the base, or hydroxide. And then because we have equal amounts, both of them will react completely. And we'll make 0.9 moles of our conjugate base, the benzoate. Okay, so that's cool, but they didn't ask us for moles of benzoate, right? They asked us for pH. Okay, and so we can start by seeing what the benzoate would do in water. So benzoate is the conjugate base of a weak acid, so it's going to be a weak base. Okay, and now we have a link to pH because we have something that results in hydroxide. Okay, and so as the saying goes, when in doubt, ice it out. But hold up, wait a second. In ice tables we put molarity, but in the ICF table we get moles. So we need to figure out what volume we have so we can get the moles of benzoate into molarity. Okay, so let's think about this. Because we knew the volume of the benzoic acid, right? This was 200 mils. And we know how many moles of hydroxide we need to add, but we didn't figure out the volume. So let's do that now. We know we need to add 0.09 moles. We know that our our base, we had, for every 1 liter, we would get 0.9 moles. So just using the molarity. And so that tells me that we would need to add 0.1 liters, which is also known as 100 mils. So our final volume is 300 mils. And so now we can take our 0.09 moles of the benzoate and put it in the 300 mils, or the 0.3 liters. Okay, because molarity is moles per liter. And so this will give us 0.3 molar and so now with our initial concentration of the benzoate, we can continue ahead and ice it out. So we'll have minus x, 0.3 minus x, ignore water because it's a liquid, 0, 0 plus x plus x, x, x. Okay, so now that we're here, we need to get our equilibrium expression involved. Okay, so we know that the equilibrium for this expression, we have a base reaction, so it would be equal to OH minus the benzoic acid divided by benzoate Okay, that's cool. We look up at our problem, and then we get stressed because they didn't give us KB, they gave us Ka, and that's not what we need, right? We don't have an acid reaction. But that's okay. We take a deep breath, and we just do one more calculation, keeping in mind that Kw is equal to Ka times Kb. So we can solve for Kb because Kw over Ka is equal to Kb. So we'll have 1 times 10 to the minus 14 divided by the Ka, which is that 6.5 times 10 to the minus 5. We find that Kb is equal to 1.54 times 10 to the negative 10. Okay, so that's not a hard calculation to do. You just have to remember to keep an eagle eye out for what kind of K you're given and what kind of K you need. Okay, so don't forget this relationship. Now we can say that x squared over 0.3 minus x is equal to 1.54 times 10 to the minus 10. And as per usual, we can ignore the x that we add or subtract when we have a k that's less than 10 to the minus 5. So then we would just multiply this over, take the square root, and we would get that x is equal to 6.8 times 10 to the minus 6. And as I've mentioned before, I like to tell myself what that is, and here our x is concentration of hydroxide. So if we take the negative log, we get POH. And that ends up being equal to 5.17. So then we just circle 5.17. But no, we have to look and remember that the question doesn't want POH, it wants pH. They want us to do another calculation. This is out of control. Okay, but it's fine. It's fine. We got it. We can do it. Okay, because it's easy to get pH from POH. pH is going to be 14 minus 5.17, which is 8.83. Phew, that's an answer. And so here it'll be D. Okay, so really be careful and try not to rush through these problems because there are just so many moving pieces, and by the time you get to pOH, you might be tempted and excited when you see a number that's an option and just anxious to move on to the next problem. But you guys are smart and you know that you need to think about pH versus pOH and know that they set a trap here by putting pOH as one of the answer choices. Okay, so practice these. Changing subjects for number 16, we're going to balance a redox reaction. And in order to do that, we have to know what's oxidized and what's reduced. And our way for determining that is by assigning everything oxidation numbers and seeing how they change. So we have our suggested oxidation numbers. So we know that alkali metals are +1. Alkali earth metals are +2. Fluorine is -1. Hydrogen is usually +1. Oxygen is usually -2. And the other halogens are usually -1. And these are written this way to be ranked in order of strictness. Okay, so we can start with the Cl2O7, and we can see that oxygen is higher on our list, so we'll assign it its preferred oxidation number before chlorine. And so this will be -2, contributing an overall -14 to the molecule. And we know that the overall sum of the oxidation numbers needs to equal the overall charge. So the chlorine needs to contribute +14. Making each individual chlorine +7. Okay. The hydrogen peroxide is going to be +1 -1. And if you're wondering why, I'll refer you to problem number 1 in this video. And then we do this ClO2-. Again, we'll assign oxygen first as -2. For overall -4. To have the sum equal -1, the chlorine would have to be +3. And there's only one, so it'll just be +3. Moving on to the oxygen, it's easy when compounds or atoms are in their elemental form because they're just going to be 0. Okay, so now we've assigned oxidation numbers. And we need to decide what's being oxidized and what's being reduced. So the species that's being oxidized will have lost electrons. So it will look like it's becoming more positive. Species that's reduced would gain electrons and appear to be more negative. Okay. So we can look at how the oxidation numbers have changed. So if we look at the chlorines, we see it went from +7 to +3. So it's a decrease in number. So it's becoming more negative and gaining electrons. Okay. So this will be what's reduced. So we can write a half reaction we're at a half reaction where we have the Cl2O7 becoming this Cl O2-. Our first step in balancing is to make sure any atoms that aren't oxygen are balanced. So we can do this pretty easily by just putting a 2 out front, because now our chlorines are balanced. Now our oxygens are kind of out of whack. We have 7 on the left and 4 on the right. So we're short 3 oxygens. And if we just add any multipliers, we'll mess up our chlorines. So the way we solve this is by adding oxygens in the form of water. So we add 3 waters to the reaction. So we have our oxygen straightened out, but now we've made a new problem for ourselves in the form of hydrogen. But that's okay, because we have another trick, which is just to add hydrogen in the form of protons to the other side. So now all of our atoms are balanced, but we have a new problem, which is that we're not charged balanced. On the left here, we're +6. On the right, we're -2. So we have a difference in charge of 8. The left is 8 units of charge more positive than the right. And so this is when the change in electrons come into play. So we'll add 8 electrons to the left to make it charge balanced. So now we have the half reaction for our reduction. Okay, next step, oxidation. So let's think about what's being oxidized. We can see that the oxygens attached to the chlorines are staying the same. The oxygen from the peroxide and the O2 are changing. So we have H2O2 going to O2. This is a pretty common thing that you see in chemistry. And so this is pretty easy at this stage because we don't have any other atoms to worry about. Our oxygens are already balanced. So we need to get our hydrogen straight. Bam. But now again, we've introduced this issue where now we're not charge balanced even though our atoms are straight. Okay. So we have a neutral left and a +2 right. And so we can easily fix this problem by adding 2 electrons to the right side. So now that we have our 2 half reactions created, we can add them together to make one whole reaction. Okay. So I'm going to start by looking at the 8 electrons on the left, and then look on the other side on this reaction and see that we have 2 on the other side. So I'll cancel the 2 and end up with 6 electrons on the left here. And then I'll have my Cl2O7, my hydrogen peroxide. But now I need to stop and think about the H+, because I have H+ on both sides. So we'll cancel the 2H+ from the right, and have 4 H plus on the left. Okay, and then we'll have our 2ClO2 minus, our 3 waters, and our oxygen gas on the right. So, if we were balancing everything in acidic conditions, we'd be done. But the problem asks us to solve in basic conditions. So what we're going to do is go through and add hydroxide to neutralize any protons. Okay? So you're not really going to have protons in basic solutions, so we need to get rid of them. So we'll add to each side 4 OH minus, 4 OH minus. And it will result in having 4 waters on the left and 4 hydroxides on the left. Or, I'm sorry, on the right. Okay. So let's erase our half reactions and look at this whole thing from the beginning, or the whole combined reaction. We'll have 6 electrons plus Cl2O7 plus H2O2 plus water, forming 2ClO2 minus plus O2 plus 4 OH minus. And this is our full balanced equation, making the correct answer E. So number 17 is asking us some true and false questions about a triprotic acid, phosphoric acid. And it gives us the Kas for all 3 deprotonations. So looking at the first statement, they say the weakest conjugate base involved is the phosphate species. So we know that the weakest conjugate base will come from the strongest acid. Okay. So we can look at the Kas to think about which one's going to be strongest. We see that Ka1 is biggest. So the original H3PO4 is going to be the strongest acid, making the H2PO4 minus the weakest conjugate base. So this one is false, and actually the phosphate would be the strongest conjugate base. Okay. The second statement says that both the HPO42 minus and H2PO4 minus are amphoteric. So let's remember what amphoteric means. It just means that you can act as an acid or as a base. So if we take the HPO4 2 minus, we know that it can go on to lose a proton and form that phosphate. But we also know that if we add water, that we can go backwards and form H2PO4 minus. Okay, so the HPO4 2 minus is amphoteric. And if we apply the same kind of strategy to the H2PO4 minus, we already know from above that we can lose a proton and form HPO4 2 minus. Okay, so it can act as an acid. And again, if we add water, we could revert to the original H3PO4. So this is also amphoteric. So 2 checks out. Okay. Looking at the third statement, saying HPO4 2 minus is a stronger acid than H2PO4 minus. And there's a couple of ways to think about this. And one is just by simply looking at the Ka's. So the dissociation of H2PO4 would be Ka2. The dissociation of HPO4 2 minus would be Ka3. And so we can see that Ka2 is bigger than Ka3, making the H2PO4 minus stronger. Also, it would make sense that HPO4 2 minus, which is more negatively charged, would be less willing to give up a positively charged hydrogen than the H2PO4 minus. Okay, so this one is false. So the only true statement here is the second corresponding to B. So here we're adding some amount of perchloric acid to some amount of lithium hydroxide and trying to figure out the pH of the solution. Okay, and hopefully you guys recognize these as both being strong. If you haven't done so already, memorize your strong acids and bases. Okay, let's write the reaction. We have HClO4 plus lithium hydroxide will form water and LiClO4. So for reactions, we want to work in terms of moles and use our ICF tables. And when we do this, we find we have 1.05 times 10 to negative 3 moles of the perchloric acid. And we have 4 times 10 to the negative 3 moles of the lithium hydroxide. Okay, then we think about our limiting reagent, which we're going to run out of first. And here we see that it's the perchloric acid. So everything is going to change by 1.05 times 10 to the minus 3 moles. we'll be left with 2.95 times 10 to the minus 3 moles of the lithium hydroxide. And I'm not going to worry about the lithium perchlorate here because it's negligible. It'll have no effect on the pH. Okay, so the only thing we have that affects the pH is this lithium hydroxide. And so for pH calculations, we need concentration. So we'll want concentration of the lithium hydroxide. We'll take 2.95 times 10 to the minus 3 moles of lithium hydroxide. And our total volume here is going to be 7 plus 20 mils for 27 mils, which is the same as 0.027 liters. Okay, but we don't really care about lithium hydroxide, we care about hydroxide, so it's worth reminding ourselves that we'll just get 1 mole hydroxide for every 1 mole lithium hydroxide. For a concentration of 0.11 molar hydroxide. So from there, we take the negative log, get that our pOH is 0.96. And our pH is going to be 14 minus that, which is going to be 13.04, which corresponds to B. Okay, in number 19, however, they want us to figure out the pH of this solution if we have this strontium nitrite salt dissolving. So let's go ahead and write the equation for it dissolving. We'll have SrNO2 in water, forming Sr2 plus and 2 nitrite ions. Okay, so strontium is going to have no effect on the pH. Okay. Strontium hydroxide is a strong base, so strontium is going to be a negligible acid. And hopefully you can see that if this is 0.1 molar strontium nitrate, that will have 0.2 molar nitrite when it dissolves. Okay, and now that we know the concentration of our weak base, we can write a reaction and ice it out. Okay, we'll have NO2 minus with water will form HNO2 OH minus. Like I said, we're going to ice it out. We have 0.2 molar nitrite, ignoring water, 0, 0. minus x plus x plus x, 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 0.2 minus x. Okay. And so now we can write our equilibrium expression. We know that Kb will be equal to x squared over 0.2 minus x. Not this again. They gave us Ka, but we need Kb. So we'll use that handy dandy reaction equation that says that Kw is equal to Ka times Kb. So our Kb will be equal to 1 times 10 to the minus 14 divided by 4.5 times 10 to the minus 4. Which is 2.22 times 10 to the minus 11. We can use that down below. We can ignore the subtracted x, and then we can multiply and square root to find that x is equal to 2.1 times 10 to the minus 6. And we should remind ourselves that this is the OH minus concentration. So when we go ahead and take the negative log of that, we'll get POH is equal to 5.68, and pH is then equal to 8.32. Bam, that's B. Okay, number 20 is asking us to pick the strongest base from the given molecules, and they tell us what their Kb's and Ka's are. So if we want the strongest base, we want the biggest Kb. So let's go ahead and make sure we have Kb's for everything that we can compare. And a reminder that Kw is equal to Ka times Kb. So Kb can be equal to 1 times 10 to the minus 14 divided by Ka, in case we need to do any conversions. So pyridine, they gave us Kb. Acetic acid, they gave us Ka. So we can get the Kb for the acetate by using this calculation. And we would find that its Kb would be equal to 5.56 times 10 to the minus 10. Hydrazine, they gave us Kb. Hydrogen cyanide, they give us Ka. We can find the Kb for cyanide, and it's 2.04 times 10 to the minus 5. Okay, so let's just find the biggest Kb, because that'll be the strongest base. And the biggest Kb is the hydrogen cyanide. In problem 21, we have a man presenting with symptoms to the emergency room. In his blood test, they find out his concentrations of bicarbonate and carbonic acid. And they want to figure out the pH of his blood. So let's write a reaction that relates these two species. So we just have H2CO3 dissociating into H plus and HCO3 minus. Okay. And these values that they've measured are going to be equilibrium values. They're not initial values because it's not like this was all dumped into his blood and then we calculate what it ends up with. These are the equilibrium values. So let's write our equilibrium expression. We know that the Ka will be equal to the concentration of H plus times the concentration of HCO3 minus, all divided by H2CO3. And they tell us what this value is. It's going to be the Ka1, 4.3 times 10 to the minus 7. And then we can use our equilibrium concentrations. So they tell us that this is going to be 2.4 millimolar. This we don't know. And this they tell us is 22 millimolar. Okay, so then we can just set this equal. We'll have 22 times x and 2.4. And you might be wondering if it's okay to leave it in millimolar. And here it will be okay because the milli of the 2.4 and the milli of the 22 will cancel out. But if you'd like, you can put those into molar values. So then we just do the algebra to solve for x. And when you do that, you get 4.69 times 10 to the minus 8 molar, and this is H plus. So then we can just take the negative log of that value to get that the pH is equal to 7.33. Which kind of makes sense. Anything too far from 7.4 would be super dangerous in the body. Okay, so this one's not too bad. Okay, this is a spin on the classic ice table problem. They want us to figure out the Ka of a weak acid given concentration and pH. Let's start by writing the reaction equation. We'll have HA dissociating to form H plus and A minus. We can go ahead and ice it out. Our initial concentration will be 0.19, 0 minus x plus x plus x, x, 0.19 minus x. Okay, Okay, and so now's the time when we usually set up an equilibrium expression and solve for x, but we don't have our equilibrium constant. So we have to get to x a different way. And our link here will be pH, because we know that 10 to the power of the negative pH will be equal to our concentration of H+, which is equal to x. Okay, so when we do this, we can just do 10 to the power of negative 4.52. Which is equal to 3.02 times 10 to the minus 5. Okay, so now we can set up our equilibrium expression. So we'll have Ka, which is equal to x squared over 0.19 minus x, except we're going to ignore this part. So we'll have that the Ka is equal to 3.02 times 10 to the minus 5 squared divided by 0.19. And drum roll, we get 4.8 times 10 to the negative 9. B. Okay. Almost there. Okay. To start number 23, I think it helps to think about what the acid dissociations look like for citric acid, this triprotic acid. So let's start by writing all three of those. Okay, so the first one will have a Ka1, which the value is given above. We'll lose one proton and have H2C6H5O7 minus. Then we can take that species and it will lose a proton and form HC6H5O7 2 minus with Ka2. Then our third dissociation will be HC6H5O7 2 minus. Dissociating to get a proton and C6H5O7 3 minus. That's Ka3. So what they're asking us about here is this Na2HC6H5O7. So let's write its dissociation. We take that species and put it in water. It will dissolve to form 2 sodium ions and HC6H5O7 2 minus. Well, hey, what do you know? That looks like the conjugate base from that second dissociation. And in this reaction, we see a base hydrolysis, right? Where we take that conjugate base and mix it with water to form hydroxide. So the equilibrium coefficient for this would be kind of like Kb2. So using our good friend, we can find that Kb will be equal to Kw over Ka. In this case, it'll be Ka2. So 1 times 10 to the minus 14 divided by 1.7 times 10 to the minus 5. Which is equal to 5.9 times 10. So in number 24, we're adding a strong base to ammonia and ammonium chloride. But wait, what do we see? What is this? Oh no, we have a weak something and it's conjugate, which means we must have buffer. Okay, that'll be useful to keep in mind later. So let's start by writing our reaction. We have our strong base, which I'll just write as OH minus, reacting with our weak acid NH4 plus. I'm going to drop the Cl because it's just a spectator, to form NH3 and water. Okay, whenever we have a reaction, we're going to use an ICF table and work in terms of moles. So I'm not going to show you the conversions to get to moles. I have it in some other problems. But we would have 0.025 moles of the hydroxide, 0.09 moles of the ammonium, and 0.075 moles of the ammonia. And we ignore water. So when we have a reaction, we're going to pick out our limiting reagent, and here it's going to be hydroxide, because we have the fewer number of moles, so we will consume all of it. And we will use up that much of the ammonium. And we'll form that amount of the ammonia. Okay, and so now this is where knowing we have a buffer will be useful, because we can use Henderson-Hasselbalch and do pH equals pKa plus the log of base over acid. I'm going to switch back because that's actually pretty annoying, but I was mixing it up. So, to find your pKa, we first need our Ka, but here they gave us Kb. So, we can use our trick with water, as we've done many times on this practice exam so far, to find that our Ka is 5.55 times 10 to the minus 10. And then we can find that our pKa is equal to 9.255. Okay. One thing that's nice about the Henderson-Hasselbalch equation is that we can use moles or molarity. So we can plug in using our pKa. So for the base, we can plug in this 0.01 for the ammonia, because that's our base. And for the acid, we'll use our 0.065 moles. And when you go ahead and solve that, you get a pH of 9.44 D. Last one. Woohoo! In this one, we have methylamine. And we're titrating it, and they want us to figure out the pH after the titration. So let's go ahead and write our equation. CH3 NH2 plus HCl, which I'll just write as H+, will react to form CH3 NH3+. Okay. Whenever we have a reaction, we work in terms of moles and use an ICF table. So the moles of our methylamine will be 0.0025. Our moles of H plus will be 0.00168. And this will be 0 to begin. And with these reactions, we have to think about what our limiting reagent is. And so we can see that that is the H+. So we'll use all of that up. We'll use that much of our methylamine. And be left with 8.2 times 10 to -4 moles. And over here we'll have made this amount of the protonated methylamine. And now we have something that we didn't have at the beginning. We have a buffer. Okay. And as we saw in the last problem too, when we have a buffer, we can use Henderson-Hasselbalch. But we need our pKa. They gave us Kb. We can find Ka using water, as we've done a number of times through this exam. And then we can get pKa to be 10.64. So pH will be equal to 10.64 plus the log of the base, which is the original compound, divided by the moles of the protonated methylamine. We evaluate that and we get 10.33, which I would call C. Okay, and so that is the end, and keep up the hard work. Just as a reminder, you can email me at vrg5018. You've been listening to Virginia. You can find me in lecture or class or office hours if you have any other questions too. Stay safe.